Good morning, students. Welcome back to the online session of Maths class, Chapter 10. I hope you all are healthy, and as a part of the corona, this is the pandemic, you all are having in your home. So be safe and stay alive. So today we are discussing about the chapter number 1, which is called real number. Now before starting the real number, we are discussing about some of the facts which is involved into the number system. For example, if we consider that, like we are considering of numbers like natural numbers, whole numbers, real numbers, rational numbers, irrational numbers, set of integers, complex number, these all are the part of the number system. So before starting the real number, which we will be discussing slightly later, which is discussing in the previous classes. Like first we are discussing about the natural number. What do you mean by the natural numbers? Natural numbers generally, if we considering that the natural numbers which is generally represented by the positive numbers like 1, 2, 3, 4, 5 up to infinite, these are the numbers which is generally associated with the natural numbers. Then it is considered as a whole number. Next one, whole number is what? It is also a part of the natural number, but the 0 which does not belongs to the natural number, which is included into the whole number. So 0, 1, 2, 3, 4 up to infinite, this is the part of the whole number. Let me discussing moving ahead, that is called set of integers, which is represented by the z. How the set of integer which is represented, like if we consider that the positive numbers as well as the whole numbers which is considered natural and whole, integers is what? It is generally included the negative terms like -1, -2, -3 up to negative numbers, which is generally a part of the integers. Now in this chapter of real number is what? It is represented by the L. It is represented by the R. So it is a collection of rational number as well as the irrational number that is generally associated with the real number. So real number in this term of this chapter, we have to discussing about this chapter like how we can find the HCF, how we can find the LCM, what is the Euclid's algorithm, what is the Euclid's division lemma method, how we can be generally factorize in a co-prime factor, how we can prove that number is a part of the irrational number or rational number, or how we can be convert the decimal numbers into a form of rational numbers, or maybe a form of it is converting into the form of rational into the integers, how that can be implemented. So first we are discussing about what is called divisions, Euclid's division lemma. Next we will be discussing about like called Euclid's division lemma. What do you mean by Euclid's division lemma? Now generally we know that if we want to division any number which require the two terms, if we want to division of any number, it generally requires the two terms. Two numbers are there. One number as a part of divisor, another number as a part of the dividend. That two numbers generally required. When you divide the two numbers, it generally gives you quotient and remainder. Like for example, if I will divide 25 with the 4, 25 that is divided by 4, how it can be find? So if 25 is divided by 4, then 6 is the quotient and 1 is the remainder, generally form. So similarly, if we want to divide any two integers, it generally gives a two form like Q and R. So same as it is in a form of real number of Euclid's division lemma, if we use the two integers a and b, which should be divided, in generally it gives two numbers that is called Q and R, which satisfied a specific equation which is called a equal to bq plus r, which satisfied a specific equation which called a equal to bq plus r, where 0 less than equal to b less than r, specifically form 0 less than equal to r less than b. So that is the Euclid's division lemma. So it is generally used to prove that numbers are in a form of 3m or 3m plus 1 or multiples of 2. That will use this type of terms. So according to the Euclid's division lemma, a is equal to bq plus r, where 0 less than equal to r less than b. It is generally considered as a Euclid's division lemma, which should be used to prove out the sums of integer are specific in a form of or multiples of any form of that we have to use to be proved. Now next is called HCF and LCM. Now according to the Euclid's division algorithm, we have also be find how we can find the HCF and LCM, that we have to use here. So what do you mean by HCF and what do you mean by the LCM? HCF generally a highest common factor and LCM is generally called as a least common multiplicator. To find out the HCF and LCM, generally we require the two numbers in which we have to compare the HCF and LCM. Generally require the two numbers. So whatever the highest factor of both number as a part of common, it is generally included as a HCF, and all the numbers which is part in the both numbers, it generally considered as a LCM, least common multiplicator. So in their form of exercise 1.1, we have to use how we can find the HCF of two numbers. Generally in your textbook, if you see that in exercise 1.1, in your textbook, if you see that exercise 1.1, there is the questions which is in a part of the Euclid's division algorithm. So how we can be find? So the first question, find HCF, okay, using Euclid's division algorithm, using Euclid's division method, okay, Euclid's division method. How we can be find? So if you want to find out the HCF using Euclid's division method, it having a generally two methods, two terms are there. Like we'll take two example, 135 and 225. Okay, this is taken as a one question, and we have to find out the HCF of these two numbers. So how we can find the HCF of these two numbers? Generally, if you see here is a two numbers is in a part of the Euclid's division lemma. If we consider that there is a two integers a and b, and which is divided by a specific number which gives you quotient and remainder, so it generally satisfied the equation a equal to bq plus r. So before division of these two numbers using Euclid's division lemma, so it is a two integers a and b. It is a two integers a and b. So first we have to verify which is the smaller number and which is the larger number. From these two numbers, we have to verify which is a smaller number and which is a higher number. So if you consider that in a 135 and 225, the smaller number is 135 and larger number is 225. So first of all, we have to use 225 as a larger number is equal to, we have to compare with the smaller number 135. Now it means 135 that is divided by 225. So how it can be divided? Like if we multiply 135 in a specific form, like 131 1za 135 1za 135, 135 2za 270. If you multiply 135 into 1, it should be 125. If you multiply with the 2, it should be 270. But what is the number here? 225. And multiply with the 2, it becomes 270. So it is quite complex to moving ahead. So it should be multiplied with the 1. 135 1za 135. Now 225 and 135, if that can be subtracted, the answer will be what? 90. Answer will be what? 90. So remainder is what? 90. Right? Clear first step? From these two numbers, whatever the number is the larger, that is ahead, it is compared with the smaller number. 225 is equal to 135, that can be multiplied. So 135 and the 135 and 225 minus 135, that gives the remainder 90. Now in the next step, we have to take in this number 135 and 90. 135 and 90. So in both numbers, which are the larger? 135 is the larger number, so I'll use 135. And whatever the remainder comes into the previous step, that can be used as a dividend. That is 90. Okay. So 90 multiply with the 135 in a specific terms. 90 ones are 90. 90 twos are 180. 180 is the larger than 135. So we have to be multiplied with the 1. 90 ones are 90 plus 45. 90 ones are 90 plus 45. So remainder is what? 45. Now next term is we have to apply with the 90. So 90 is equal to 45 is the remainder, 45 into 2, and remainder will be 0. Remainder is what? 0. So in which the step will the remainder will be 0, there we have to stop. Okay, when the remainder will be 0, then we not need to be divide the numbers. So what is the HCF? If remainder will get the 0, what is the HCF? So the previous term of the remainder, that is what? 45. So HCF of 135 and 225 is equal to 45, right? So by using this term, देखो simply we have to also use the division formation like the another form. So if we compare the two numbers like 135 and 225, it should be easily divided with the specific form of Euclid's division algorithm. Also we take another example like 867 and 255. We'll take another example like 867 and 255. Okay. Now also we have to, this question we find out by the Euclid's division algorithm. How we can be find? So see that 867 and 255. If we compare the two numbers, 867 is a larger number and 255 is a smaller number. So therefore 867 into 255, right? 255. Now we have to multiply 255 with a certain part of the multiples. 255 ones are 255, 255 to the 510, 255 is the specific numbers. So it should be, if multiply 255 into 4, it goes the number beyond the 1000. If you multiply 255 with the 4, it generally goes beyond to the 1000. So we have to multiply with the 3. So 255 into 3. Okay. Now what is the remainder is remaining? 102. If we multiply 867, that's divided with the 255, 255 into 3, and remainder will be 102. Now in the next step, 255 is equal to, now we have to multiply with the 102. 102. Now 101 1 101, 102 into 2, that is 204. And if multiply 102 into 3, it becomes 306. So 306 is larger than 255. So we have to multiply with the 2. So 102 into 2, that is 204, and 51 is remaining. 51 is what? Remaining. Now in the next step, we have to take on 102. 102. 102 is equal to, now in the next step, what is the form is remainder? 51. So 51 into 2, 102 plus remainder will be what? 0. Remainder is what? 0. When the remainder is 0, the previous form of remainder, that is 51. So HCF of 867 to 55 is what? 51. So that is a simple Euclid's division algorithm. By using this, you can find the HCF of the number. So HCF of 867 and 255, that gives you 51. Simple. So that is generally called as a Euclid's division algorithm method, in which by using this method we can find the HCF of two numbers. So if you want to find out the HCF of two numbers, general circumstance is it should be two numbers which is compared to each other, the larger number which is divided by the smaller number, and in what forms of the multiple it can be multiplied, and whatever the remainder is remaining, that should be in a form of 0. So A is equal to BQ plus R, that is the form of Euclid's division algorithm. So now it is a simple form. Now how? It is generally called as a Euclid's division lemma of algorithm. Now if question is slightly given into the different form, if the question is slightly given into the different form, for example, if we consider that any even positive integers generally is a form of, or odd positive integers is form of 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. How we can be proved? Let me take one example. So positive integers generally, if we consider that, so that any odd positive integers is in a form of 6 cube plus 1 and 6 cube plus 3 and 6 cube plus 4. How it can be proved? Simple question is there. Using Euclid's division lemma, we have to prove that. How we can be proved? Because this type of questions are generally not asking in the examination, but certain times it can be also be asked. So how it can be proved that? One question is that so that any odd positive integer, okay, is in form of 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5. Okay, this is the one type of question. So that any odd positive integers is in a form of 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5. How it can be proved? So generally we studied about Euclid's division lemma. When we start this chapter, we're discussing about the Euclid's division lemma. So in Euclid division lemma, any two positive integers in a form of a and b, which should be as a part of the dividend, which gives as a part of the quotient and remainder. So it gives you a is equal to bq plus r, where 0 less than equal to r less than b. This is a standard form of Euclid's division lemma. Using that method, we have to prove that any odd positive integer is formed in of 6q plus 1, 6q plus 3 and 6q plus 5. How we can be proved? So before prove that, so we have to be suppose any number. We have to suppose any number. So for let me example, let q is any positive integer, a is a positive integer and q is some integer, that we have to suppose that. How we can be solved? So let a be the positive odd integer, a be the positive odd integer, positive odd integer, okay, and q is some integer, okay. So let a be the positive odd integer and q is some integer. So standard Euclid's lemma is what? According to the standard Euclid's lemma, a is equal to bq plus r, where 0 less than equal to r less than b. That is the standard Euclid's division lemma algorithm. But if we see that the question is given, we have to prove that odd integer in a form of 6q plus 1, 6q plus 3 and 6q plus 5. So if we consider here bq and here is what? 6q. So let we have to take b is equal to what? 6. We have to take b is equal to 6. So let b is equal to 6. We'll take b is equal to 6. Right? So when you take b is equal to 6, so remainder is what? Here is what? So r is equal to 0, 1, 2, 3, 4 and 5. How this value that can be written? R is equal to 0, 1, 2, 3, 5. If we consider that 0 less than equal to r less than 6, b is equal to what? 6. So we have to take a reminder's value from starting from the 0. Less than equal to, it means what? We have starting from the 0, and less than 6, it means we have to carry on with the 5. So remainder is 0, 1, 2, 3, 4 and 5. So now whatever the remainder you get, that remainder that should be applied into the formula of a is equal to bq plus r. So now a is equal to, first we'll write 6q. Instead of b, I'll write 6. A is equal to 6q plus remainder 0. So no need to be write 0. Okay. Next a is equal to 6q plus 1. Then a is equal to 6q plus 2. Right? Once again, here I will write here a is equal to 6q plus 3. A is equal to 6q plus 4 and a is equal to 6q plus 5, right? See that if we consider that, let b is equal to 6, so remainder is what? 0, 1, 2, 3, 4 and 5. Remainder is what? 5. And if we apply the value of 0 into the form of a is equal to bq plus r, so remainder will be, we have to add it in this formula, a is equal to bq plus r, where remainder is continually moving from 0 to 5. So a is equal to 6q, a is equal to 6q plus 1, a is equal to 6q plus 2, a is equal to 6q plus 3, a is equal to 6q plus 4 and a is equal to 6q plus 5. Those are the general questions we have to written. Now, but we have to prove that any positive odd integers is in a form, odd positive integers. So if it will be positive odd integer, it cannot be in a form of 6q plus 2 and 6q plus 4, or maybe in a form of 6q. Okay? If we see that a is equal to 6q, 6q plus 4 and 6q plus 2. If remainder is a even number, it means that particular form is in a form of even number. So we see here, so a is positive odd integer. A is positive odd integer. Okay, odd number, it means what? Always be remainder will be what? Like 3. 3 is odd number. How it can be? 2 plus 1. Remainder is odd. Like 7. If we consider 4 plus 3, 3 is what? Odd number. So if the remainder is generally in a form of odd number, then it should be a form of odd. But if we seen that here is a is a positive integers, but if we seen that 6q and 6q plus 2 and 6q plus 4, okay, if we seen that 6q, 6q plus 2 and 6q plus 4, these are the even numbers. It is in a form of even numbers. So, but 6 are even numbers. Even numbers. So, obviously, the remaining term, which one? 6q plus 1, 6q plus 3 and 6q plus 5. So, hence 6q plus 1, 6q plus 3 and 6q plus 5 are odd integers. Are odd integers. So simply, if you want to prove that any positive odd integers in a form of 6q plus 1, 6q plus 3, 6q plus 5, by using this Euclid's division lemma, we have to prove that any positive odd integers are in a form of 6q plus 1, 6q plus 3 and 6q plus 5. Now, let will take another one example how to prove this Euclid's division lemma. Before that, let's take one example like an army consignment. Like in army consignment, there is total 616 members. In army consignment, there is total 616 members. And generally, behind of each members, that is each and everyone 32 members. Total 616 and 32 members are specifically behind him. So, how many numbers of column which can be created by the army consignment? So, maximum we have to use. How many maximum numbers? So, if in a question, if word is given, how many maximum or maximum word or maybe minimum word. So, if maximum word is given into the form of two numbers, we have to use the HCF, and if minimum number is given, we have to find out the LCM. So, in that question, I will give you the total members is 616. Total members is what? 616, and we have to create each column having the 32 members. Okay. So, I will write here total person is 616. Okay. Now, each column having the numbers 32. Each column having 32. How many maximum columns? So, we have to find out HCF. We need to find HCF of 616 and 32. Why HCF? Because here the word is given how many maximum number of column that it can be created. So, maximum word is there, it means we have to find out the HCF. Now, this using Euclid's division lemma, we can find the HCF. So, there is two numbers 616 and 32. So, 616 and 32 that we have to be divided as a Euclid's division lemma. So, how we can be divided? So, therefore, 616 that is divided by 32. Okay. 32 into 19, 607 plus 9, 616. Next is 32, 9 3s are 27 plus 5. Okay. Now 32 is what? 9 3s are 27. Okay, 1 second. 32 into 10, 320. 1 second. This is remainder is 8. 608. 9 2s are 18, 8. So it should be 8 here. Okay, remainder is 8. So now 32, 8 4s are 32 plus remainder is 0. Now if we get the remainder is 0, the previous term of remainder, that is called HCF. The HCF is what? 8. So HCF 616 and 32 is equal to 8. So we have to create maximum 8 columns of the army consignment. So that is, if word is given maximum, then we have to use to find out HCF. Now, still I will use one question how to prove Euclid's division lemma, then we move ahead for the HCF and LCM, how that can be find HCF and LCM due to the factorization method. So, that is the question, how we can be find the Euclid's division lemma method, how we can be find. So, there is a question which is in a part of prove that. If you want to find out the proof in a form of prove that numbers. So, let me take one example. Okay, we have to prove by using Euclid's division lemma. By using Euclid's division lemma, we have to prove that the square of any positive integer is generally in a form of 3m or 3m plus 1. Okay. So that by the Euclid's division lemma algorithm, square of any positive integer in a form of 3m and 3m plus 1, that we have to prove. How we can we prove that? Generally see that. So that square of any positive integer, is in form of 3m or 3m plus 1. Okay, right, we have to prove that. So by using the Euclid's division lemma, we have to prove that square of any positive integer is in a form of 3m or 3m plus 1. How we can be find out? So we have already know that Euclid's standard division lemma is generally in a form of a is equal to bq plus r. That is the standard formula. So using Euclid's, so a is equal to bq plus r, where 0 less than equal to r less than b. This is the standard division algorithm. So let b is equal to what here? 3m form or 3m plus 1 form. So we have to take an m is equal to, so let b is equal to 3. Okay. If we take b is equal to 3, the remainder is what? So remainder r is equal to 0, 1 and 2. 3 possibilities are there. Case 1, case 2, case 3. So now, so therefore, it should be converted in a is equal to 3q, a is equal to 3q plus 1 and a is equal to 3q plus 2. Because maximum remainder is 0, 1, 2. So a is equal to 3q, a is equal to 3q plus 1 and a is equal to 3q plus 2. But what we have to do that, okay, we have to find out the square of this integer. We have to find out the square. So we have to find out the square. So 3 situations there, case 1, case 2 and case 3. So let me start it from the case 1. So case 1. Now case 1 is what? A is equal to 3q. Case 1, a is equal to what? 3q. So we have to square off both hand side. So it becomes a square is equal to 3q square. A square is equal to 3q square. So it gives you a square is equal to 9q square. A square is equal to what? 9q square. So we'll take here, I'll write here, okay, by using the sign. A square is equal to 9q square. It means a square is equal to 3 into 3q square. I'll making 3 as a common from here. So 3 is a 9q square. So let here 3q square is equal to m. I'll take 3q square is equal to m. So therefore a square is equal to 3m. So if a square is equal to 3m, so obviously a is equal to in a form of 3m. Now we'll take it from the case 2, that is 3q plus 1. Now case 2, that is a is equal to 3q plus 1. A is equal to 3q plus 1. So we have also find the square of this number. So therefore a square is equal to 3q plus 1 square. So it is term of a plus b whole square, a square plus b square plus 2ab. Okay. So a square is equal to 9q square plus 6q plus 1. Right. So therefore a square is equal to, I will also take 3 as a common, 3q square plus 2q in bracket 1. Outside of bracket is 1. So 3q square is plus 2q. Let me take m. 3q square plus 2q is equal to m. So a square is equal to 3m plus 1. Right. So if we see that, if also prove that 3q plus 2, it is also in a form of 3m. So it should be proved that by the Euclid's division lemma, square of any positive integers is generally in a form of 3m or 3m plus 1. So what we studied about today? Only we studied today what is called Euclid's division lemma, what is called Euclid division algorithm, how we can find HCF and LCM, and using Euclid's division algorithm we find the HCF of two numbers as well as we have to prove that Euclid's division lemma, how the numbers are generally in a form of 3m plus 1, 6q plus 1, etc. From today, that is the only topic discussing. Now next we'll start this chapter from tomorrow, that is a part 2. Today we'll take part 1. When we start to part 2, we're discussing about how we can find the HCF of LCM of two numbers by mapping of Euclid's division algorithm, or also by using the co-prime factor method. And also we're discussing about how we can prove that rational numbers and irrational numbers. Okay, for today we're discussing about till, we'll meet tomorrow, we're discussing about the ahead. So till today, that is the chapter we're discussing. Next we're discussing ahead from the methods, how to find the roots values. So till today, that is enough for you. We'll meet tomorrow. Okay, bye.